Okay, cool. So let's move on to extended surfaces. All right, so far what we've talked about in 1D conduction is heat that's moving in one coordinate, maybe it's x. We've done a lot in cylindrical coordinates with r, but heat is really truly only moving in one direction, right? You might have a plain wall, or you have a wall that has adiabatic boundaries on the top and bottom, and there's no reason for heat to flow in any direction other than the primary coordinate that we're modeling the temperature distribution. Extended surfaces are now kind of the next step in this analysis, where we now relax that assumption that we can't have heat flowing in other directions. And in fact, this is something that you're seeing on the homework that you're doing right now. Okay, the homework that you're doing doesn't actually require this analysis we're going to go through to a large extent, but it's kind of the same concept. So for an extended surface, the idea is that, let's see here. So if I'm a little bit of heat and I'm at the sort of base, I'm at the base of this fin, right? So this is a big piece of metal or small piece of metal, and it's attached to some base, right? And an extended surface is just an approximation that we're going to make that allows us to model something as 1D. So if I'm a little piece of energy and I'm right here at the base, you know, if I'm going to move out to the surroundings, right, the surroundings being out here at T infinity, let's say, it's no longer true for this type of surface that I would just move in the x direction, right? You may have this happen where some little unit of heat, if such a thing exists, would get here and then, you know, go off to the surroundings. But for a lot of the heat, it's going to actually kind of do this, right? It's going to go out and be lost to the surroundings off the edge of the surface. So, all right, we've got our coordinate system here, right? We said, okay, we have an x, and we have a y. So this really is not a 1D problem by any stretch of the imagination. It's definitely a 2D problem. You definitely have heat flowing in both the x direction and the y direction. Okay, but what an extended surface approximation is trying to do is it's saying, if I can make the assumption that yes, heat is flowing in both directions, but there's only a temperature gradient, or there's only a difference in temperature that's significant in one direction, then I can model this as a 1D surface or a 1D problem. Right? And think about what that kind of means, right? So if I, let's see, so if I think about this in terms of a resistance, I have, starting here at the base of this fin, I would have some resistance to moving in the x direction, right? We'll call that R conduction. Oops, where'd my pen go? R conduction in the x direction. Okay, there's also a resistance to get to the edge, right? So you go like this, and you'd have some R conduction in the y direction. Right, once, if you're that bit of heat and you've gone some distance x and some distance y, that's not the whole story, right? You still have to get to the surroundings. Okay, so then there's an addition. Oops, sorry. There's an additional resistance here associated with the surroundings. We'll call this, for this case, it's just convection. So R convection. All right. This is kind of the way to conceptualize the problem in terms of resistances in a very approximate way. But if we think about what's happening now, let's say in this problem, I have a conduction resistance that's significant, and I have a conduction resistance in Y that's significant. So both X and Y are significant. What would I expect to see in my temperature distribution, right? Think about, I mean, and the hint is up in the corner. Right? So what would I expect to see? Well, I would expect to see, here we are starting at the base, right? Up here at the base, this is our uniform temperature up at the base. As I move along this position, this coordinate X, right? As I move in this direction, I would expect to see the temperature drop because I have a resistance there. And what do we see over here? We see, here's our base temperature as a function of position, X over L, it's dropping, right? So yeah, this makes sense. We're seeing a temperature drop due to a resistance in the x direction. What would I see in the y direction? Well, if y over here, if this resistance is significant as well, I would also need to see, hopefully, okay. I would also need to see a temperature drop in the y direction. And we see that here. We see there is this temperature difference here between the center line, which is right here, right? This corresponds with right that the center of the fin and the edge of the fin. So I see a temperature drop there. That's significant. So this, if we were to try to say that this is a 1D model, we'd be wrong, right? Because what would a 1D model imply? A 1D model would imply, if I pick a position, let's say I pick this position here. A 1D model is saying I have a constant temperature profile as a function of one of the two coordinates. So if I were to say I want a 1D model in X, I'm saying there is no temperature distribution in Y. It's the same thing all the way across, right? So an extended surface approximation is a special set of circumstances where, because of the resistances in the problem, we can, in fact, say, this is a 1D problem. There is no temperature distribution in one of the two coordinates, even though heat is actually flowing in both coordinates. Okay. Does that sort of make sense to everybody so far? Okay, and this might be something you've seen before in previous coursework. Okay, so how do we actually decide what's good enough, right? If there's going to be heat flow, there has to be a temperature gradient. So you'd never have a perfectly level temperature profile like that. But what would be good enough? Like, what is the criteria that we can use to decide is a 1D approximation a good approximation or not? So we would want to look at what is the resistance ratio, or the ratio of resistances in the direction that's sort of that second direction. So what do I mean by that? So let's first let's look at this conduction resistance in Y. All right, so remember our conduction is equal to the distance to conduct, right? So the distance to conduct in this example is something like thickness over 2, right? And then it's divided by the conductivity of the material times the cross-section area available for conduction. And that, in this problem, it is what? So this dimension is W times L, right? So W times L. Right, so that's our conduction in the Y direction. And then we have convection in the Y direction as well, or convection to the surrounding. So convection here is going to be, our convection is going to be 1 over H bar times A, and A is W times L. Right. So we have now these two resistances. And if you really think about it, what we're trying to do, if we want to justify that temperature distribution up there being flat, what would the ratio have to be? Like, where is all the temperature drop going to have to happen? The temperature drop is going to have to happen in the resistance to the surroundings and that transfer to the surroundings. So we would say we want the ratio our conduction Y divided by our convection to be really small, right? And this has a name. This is called the Biot number, BIOT, which is often referred to just as BI. So BI is equal to this ratio, right? And if this ratio is much less than 1 being, let's say, like 0.1 or something like that, not 0.9, but something small, then we can justify the assumption that this is in fact a 1D problem, and we can go through the analysis and come up with a 1D solution for temperature that is a pretty accurate representation of what's actually happening. Okay, so the Biot number is this resistance ratio, but really it's if you look at what we're doing here, if we look at what we're doing up here in this plot, what we're also saying is it's kind of just the, approximately the ratio of the temperature drop through conduction in the Y direction to the temperature drop due to convection. So if we can calculate or estimate those temperature drops, it's basically the same thing as the resistance is, and if it's small, then we're okay. And we can move forward with our 1D analysis. Okay. Let's see. Okay, so let's see if skip this one, I think. Yeah, we already talked about this. Okay, so one other kind of minor thing to point out just before I move on. So in this example, I said, my distance to conduct was this, right? This is my distance to conduct, which was thickness over 2. Why did I say thickness over 2? I mean, you could come in here and say, well, actually, like on average, the heat's going to be conducting from maybe thickness over 4 on average. Like that would be a much more reasonable thing. Okay, so then you go through and maybe I first calculated Biot number to be 0.01, and you come through and it's the Biot number is 0.02 or 0.005 or something like that. Is that important? Right. We don't actually use this number anywhere in our solution. This is a method that we're going to use to justify an assumption we're going to make that allows us to get a solution. But you will never use the Biot number directly in any solution. So if you come back and we're arguing about 0.01 or 0.02 and which one it is, both of them are much less than 1. And that's the point, right? Yeah, question? Yeah, so the generally accepted threshold would be like 0.1, I'd say, but it's going to depend on what you're trying to answer. So think about what it means to have a difference or a 0.1. So like if we look back here, so if I came in here and I said my Biot number was 0.1, what I'm saying is, I'll draw this way. So I'm saying this temperature difference here, this one here, is about 0.1 of the total temperature difference from here down to the ambient temperature. So if you're okay with that, so it's like saying 10% error, right? You're okay with a 10% error in your temperature on the surface, then fine, then you can just model as 1D. If what you're trying to do is go through and derive a model where you have a very exact representation of temperature at each position X on the surface, then you probably want something like 0.01 or 0.001. So it's a tool that you have to use, but you have to put it in the right context, I would say. That, by the way, is probably the most messed up concept from 364. Is people really have a hard time with this kind of fuzzy thing called the Biot number, and but it's just a tool that lets you justify getting to the 1D solution. Okay. What was I saying here? Right. So yeah, that was the point. Okay. The other thing to point out here is we came up with a Biot number definition for our fin, our specific fin, the one that only has convection to the surroundings. What if we had a fin like this, where it's convection and radiation? So then what do? Well, really what we care about is this thing up here, the kind of words that are written here. So we want to compare a resistance that we want to neglect. In this case, we want to neglect any temperature drop in the y direction, the direction that's normal to the primary heat flow. Okay, we're trying to neglect that temperature, that resistance. So we put that in the numerator, and then we want to look at the resistance from the surface to the surroundings as kind of the baseline comparison. Okay, so in this case, we would say then we've got these two things. So now our resistance here becomes the parallel combination of both of these things, convection and radiation in parallel. So actually our Biot number for this would be defined as R conduction in the y direction divided by 1 plus R convection over 1 plus R radiation, right, to the -1 power. Right? And this, if you evaluate it out, it would be, I guess, thickness times h bar epsilon sigma 4t bar cubed divided by 2k. Okay, so that was for just for this example. okay, so this looks different from the Biot number you would get if you just evaluated it the previous way. Okay. Oh, you know, we might also say something like this. So this is something that came up last semester. So let's say we have a coating on this thing. There's like some rubber coating or plastic coating or something. People always get confused. Okay, there's still conduction happening through this coating. So is that part of my numerator or part of my denominator? Okay, so it depends if we're trying to neglect, if we're modeling the temperature distribution in the fin, in the metal, then the coating is part of the surroundings. It's part of the thing that the heat has to get through to get to the surroundings. Just because there's conduction happening doesn't automatically make it part of the thing you're trying to include in your temperature model. Okay. Okay, that's maybe enough on that. All right, so let's look at kind of a example here that would compare a situation where our conduction is large relative to the problem that we're dealing with versus small, right? And look at how it kind of works. And this goes back to the question we just answered. So if we were to plot here, so let me just do this. We have dimensionless temperature. Let's say this is T, the temperature minus the surroundings temperature over TB minus T infinity, right? This is kind of a fractional temperature. This temperature is going to be between 0 here and 1, right? It has to be between these temperatures. And then down here, let's do dimensionless position, 0 to 1, and this will be X over L. So I want to plot or kind of anticipate what the temperature profile is going to look like as a function of position at both the center line of the fin and at the surface of the fin under two assumptions. So let's first look at an assumption where this conduction, right? So let's say our conduction Y is approximately equal to our convection. Right? And in that case, Biot number is not going to be 0.1. It's going to be much bigger than that, right? 1, let's say. So what would I expect the plot to look like? So first, let me draw. Let's see. Let me draw the center line temperature. So let's say it looks something like this. Right, so this is a temperature. This is my temperature as a function of X at Y equals 0. Right, this is Y. Right, this is Y equals 0 here. So what would I expect my surface temperature, if I draw my surface temperature, what do I expect that to look like? Right, is it going to be along that line? Is it going to be above the line? Is it going to be below the line? Any guesses? Right, we have a temperature drop between here and here, right? So it's going to have to be below it the whole way. And how far is it going to be below it? Well, if these are about the same, I would expect that the temperature is going to be, significantly lower. Right? So it might look something like, let's see if I can do this very well. This, right? Oh, that was bad. Let me try that again. Maybe I need to turn around. All right, so it's going to look something like this. Right, so there's a significant delta T. So this is the delta T between Y equals 0 and Y equals thickness over 2. That's a temperature drop between those two positions. Okay, so that's the assumption here where they're about the same. What about the case where our conduction Y is much less than our convection? That's saying that the resistance to conduction in the Y direction is really low. It's really good at moving heat. It's really good at taking heat from that center line, moving it out to the surface. But when it hits the surface, there's a big impedance, right? There's a big, like resistance in the way of getting from the surface to the surroundings. So that means all the temperature drops going to be happening outside of the domain, right? So like if I draw this again, I have my temperature as a function of, right, so this is now T of x at y equals thickness over 2. So now if I draw my my temperature at the surface, it's going to be really close, right? It's going to kind of track along this. And maybe something like this. So now this is at thickness over 2. Okay. Now it's not good. They're not going to be unless your conductivity is infinite. Basically, if that Biot number is 0, then they would exactly line up, right? But there's always going to be some minor temperature drop. But think about what we're doing. We're saying now, if I have this case down here, right? This is my case. I can say I can pretty much approximate any temperature just as a function of x, right? I can come up with a single curve that gets pretty close to both of those extremes, both the center line and the surface. Okay, yeah.
The red line still at y 0?
Oops, sorry. Yeah, I wrote that backwards. My bad. So yeah, this is at y equals 0, and this is at thickness over 2. Sorry about that. Right, so yes, at y equals 0 at thickness over 2, we're really still close to each other. So I can come up with a single curve that's just a function of x and be happy with that. Okay. All right, so then that's thinking about resistances in the x or in the y direction. But what about resistance in the x direction? What about resistance from the base conducting along the x direction? What's going to happen? Or maybe we can sort of step back and think about what would be the temperature profile in both of the extremes where conduction in the x direction, the resistance there is really high versus when it's really low. Okay, so again, let's kind of just conceptually think about this before we get into actually deriving solutions. So here we have, right, our conduction in the x, which is the total length it has to go, L over K times thickness times W, and then we have convection, right? And by the way, this is normally H bar times perimeter. So why did I just write H times W times L for convection? Well, we say here, we're assuming W is much, much bigger than the thickness. So this simplification here is just kind of an approximate solution that's good enough. Right? Okay, so what's going to be the case? Let's see, I've got my dimensionless temperature, T minus T infinity over T B minus T infinity, and this goes from 0 to 1. And then I again have my position x over L. So this is x over L from 0 to 1. All right, so first let's think about a case where the resistance to conduction in the x direction is really low. Right? What might cause that? Right? This case here. Let's say that's really low. What might cause that resistance to be low? Well, conductivity is really, really high, or the ratio of the length to the area for conduction is really low. So think like make the fin really, really short. Okay. So under those circumstances, what kind of temperature drop would I expect to see in the x direction? Really, really low resistance. Right? It's a really good heat mover. I would expect to see something like, I don't know, like this, right? Where as a function of x, I'm really not losing that much temperature as it moves along the fin, right? What would I expect to see on the other hand? Let's say conductivity is really close to 0. So it really has a hard time moving. Right? It probably would look something like this, right? You're going to lose all of your heat right away. It would much rather send the heat out to the surroundings than it would conduct along the x direction. Okay, so those are kind of the bounding cases that we would expect. And we'll kind of come back to this plot as we get a little further on. You know, and if I were to pick some intermediate thing, right, you might think of how you could draw it, but you might have an intermediate curve that would look something like this too. Okay, we'll come back to interpreting what this plot means, hopefully at the end.